give you calipers. You guys know how to use calipers?
Yeah.
Great. I have to ask. I don't know what classes you guys have taken already. So make sure it's zeroed. We're going to measure in inches. I need you to measure the thickness, which is parallel to this notch over here. So this would be the thickness.
Okay.
And then I need you to measure the width, okay, which is perpendicular.
Oh, it's not the same, it's not a perfectly square
It
thing?
may be perfectly
Okay.
square,
Just
but
gotta
you need
make
to
sure.
know.
Okay.
So I need you to do it for three of them, right?
Okay.
One for steel, one for aluminum, one for... I've had different ones for each group, but I want to let the groups actually sort of discover it for themselves. In the meantime, I will go fill up this liquid nitrogen, and then I will show you the tutorial later. And we'll talk more about the machine and the test in general.
Are you measuring the width or the thickness? What is this, the width or thickness?
This is the thickness. This one is broken. 0.368. Can you write it down, please?
Yeah. What is it?
0.369.
6'9". And this is width?
Yeah.
Okay.
Same thing.
No, zero it first.
No, it doesn't have to.
You don't have to zero it each time?
It's already been zeroed, yeah.
Okay, cool.
It's just when you initially start it up, it sometimes doesn't ring correctly.
Alright.
So, but yeah.
So it's the same thing?
Same thing, yeah. So that was steel.
And this was steel?
Yeah.
Which color? Alright.
This is aluminum.
Oh. That was 0.374. This is width?
Yeah.
I'm going to take one of these, that you guys are not touching.
This one's a little bit different.
It's the same thing.
0.5. You see how it's just ever so slightly different.
Okay. 0.375.
And as I put this in, and while you guys are measuring, it's going to boil on the inside because it's a lot hotter than the actual liquid nitrogen.
Okay.
Good. This is cast iron.
And then we let that sit.
Okay.
Same.
So they were the same? Or no?
So the only one that was different was just like the
Thickness.
aluminum. Was everything.
Thickness and width.
I gave it to you.
Oh, I need to put mine there too. Sorry.
If you have one, then once you're done measuring.
Do you want me to take it better and shut it off, or just need this or no?
Yeah, I'll just hold
Yeah,
into it for now, yeah. I'm going to take it out before I put it away. Based on this. So this is an old arm for this machine. Okay, the machine would go and it would impact it as well. Now, this started breaking over here. The fracture started here. Then it went to here. Then it ended here. Do we know why it went here? What could possibly have been here that caused it to cause the fracture to move there? Right? It doesn't matter where the fracture starts.
Microfracture there?
Well, it could have been microfracture, but there's also something else there.
Oh, there's a hole. Okay, so
There's a hole. What is the hole acting? Do you know what? Have you heard about stress concentration?
stress concentration? Yeah.
So the hole is acting like a stress concentration. So what happens is this fracture might start somewhere else, but now it goes to the hole because the hole is the easiest place for it to break. What happens in nature is that nature tries to go for the thing that requires the least amount of energy. It's why you don't want to touch the ground and the power wire at the same time because the electricity is looking for the path to the least resistance down to the ground. Right? It's the least energy required. That is how nature works. So it starts here. It doesn't just keep going. It actually finds that the least amount of energy would be to go to the fracture, to the stress concentration here, because it'd be the easiest to break it. Right? What happens over here? There's a stress concentration here. That's the hole. What is over here? Why does it go straight up here? Is there anything on this side that would cause that? Exactly. This is a fillet. This is a fillet. A fillet is a much higher stress concentration actually than even the hole. So what happens is it goes to the hole, it says, I like this, but then it finds an even better one. And so it goes straight to there, right? You're looking for the minimum amount of energy required to break this, and that's what it was. This was the path. So it might have initially cracked due to like a stress fracture or something that was inside the material. Maybe that was a weak point in general. It's hard to tell, right? But then it gets here, and then it goes here. So you can sort of figure out where a fracture might happen based on stress concentrations. We try to avoid these as much as possible, right? When we design something, especially something that has to go under impact. This is an important bit. This is cast iron, so actually the crack is a little rough as well. You know, very similar to a brittle crack in this case. There's almost no ductility here either. So, all that being said, why do we have a notch here? Now, we place it in the machine with the notch facing this way, and the impact goes here. So what is the point of this notch?
So it goes straight across because there's you have the stress
it hits here.
stress to be the maximum at that point.
So this is, what is it?
Stress concentration?
Yeah, just like the fillet. This is a stress concentration. What is the point of having a stress concentration?
It's to ensure that when it breaks or if it's brittle, that it happens in that location.
Yes. One point is that we're trying to control its location. We want it to break here and not somewhere else. The material might be weaker here than it is here, but if we put a stress concentration, the fracture is going to go straight to there instead, right? It's going to start cracking from here. Now, what happens is we're pushing here. So, right, imagine you're pushing up against here. Where's the tension? Where's the compression? Imagine this is bending, where I'm pushing up in the center.
So
Which side is under tension? Which side is under compression?
The compression is the bottom, the tension is on top.
Exactly. This is going to split apart, almost like scissors. Well, it's almost like a piece of paper, right?
Yeah.
So if you get a little notch like this, it'll just split, starting from this area. Okay? What is the other point of having stress concentration?
Less force to break?
No, it's not really what we're looking for. As long as the stress concentration is the same, we're looking for around the same amount of force. Really, the other main purpose is to make it break. It's possible the whole thing would just bend. It might not even fracture at all, and then we're not seeing the fracture. We're just seeing bending, right? Especially on a really ductile material like steel, you'll see that it's really like trying to stay together. So by doing this, we're causing it to break at all. You know, we're trying to force the fracture. You know, if you wanted to force a fracture in something, you put a stress concentration there to make sure that it does fracture. So not only we're controlling where it is, we're also making sure that it does break. Okay? So, the way this is going to work, I'll show you the machine. This is the impactor. We've got the actual arm over here and then a weight here. This is a velocity sensor. So the way that this measures velocity, there's a sensor right here. It reads one and then the other, okay? And if you know the distance between the two, how do you figure out the velocity? Or I guess in this case the speed, because the direction is understood. How would you figure out the speed if you knew the distance from one place to another, right? You know x2 and you know x1. How do you figure out the velocity?
time.
Time, exactly. You put x2 over x1, t2 minus t1, right? You're differentiating your position, you get your velocity, right? So, if you were on a highway and you saw a mile marker, right? And you know that each mile marker is exactly 1 mile apart. If you count when you see that first mile marker, and you count at the same time you see the next mile marker, based on that, you know exactly how fast you're going, right? Especially if you're going at consistent speed. So recalculate. We see it, the amount of time it takes us to this, the amount of time it takes us to this. We know the distance, we calculate the velocity, right? Make sense? It's a very easy way to sort of calculate velocity. That's generally how we do it. Now, we have a wire here. This wire goes to a force sensor over here. Okay? This force sensor, it's right behind where the actual impact will happen. That's the force sensor. It's connected by that wire. And it will measure our energy as we go into it. It'll measure the force, and then we'll convert it to energy. Okay? This is all electricity, right? So it's all voltage sensors. So what happens is you'll see the graphs are not so clean because voltage can change a lot. But the basic idea is they're just being not so consistent. Like each thing, it's not perfect. Right? The voltages are always changing. You know, the wire, where the wire is, and change it, etc. Lots of things affect voltage. Interference. All right. So let's say you didn't have all this. How would you measure velocity? So as you get hit, this thing does move. And this will move with the arm. How would you measure the amount of energy that goes into the sample? The sample will sit over here. You have the weight, you have this, you know the height. So what does that mean? How much energy will go here?
You said there was no potential energy is kinetic.
Yes, so what would you do? Imagine you knew the height on this side. And maybe you know the height on this side.
You have the mass.
You have the weight of everything, yeah.
Yeah, so you know that.
Acceleration due to gravity. Acceleration due to gravity, right?
Right, but we're just dealing with energy, right? You know the energy, right? So how can you calculate the energy that goes into that impact?
Isn't it PM? Is it what's the equation for potential energy?
Potential energy at the top that's going to be, so the value at the bottom is going to be 0. So you know that without significant energy at the bottom.
Okay. So, but better, potential energy here, what do you have on this side after it's already hit?
The kinetic energy, like
Starts
tra-
here, goes up here. Okay? Do you know anything about the energy when it's over here?
Yeah, so because you have, it starts at this position, right? As you're going down there, you're gaining kinetic energy.
Yes.
So it goes together.
But what do you have over here again?
Potential energy.
This is a pendulum. What do you have here? Right, so explain.
So at this point, it's going to be higher than it's at this point. Because
Yes.
it's going to lose energy.
What is taking that energy?
The impact.
Exactly. You don't have to go so fancy with it. I know potential energy here. I know the potential energy here. The friction is pretty negligible. You see, it's smooth. It's pretty smooth. So we'll ignore the friction. Where does all the energy go? There. Into the impact. You don't even have to go into how you calculate potential or anything like that. You have potential energy here and here. So you could do this by hand. It doesn't tell you what the energy is through the impact. It tells you the whole amount of energy that went into it. And so we'll see that at the graph, that will be the energy at the end of the impact. Okay? So even if you didn't know the force sensor, even if you didn't know the velocity, you don't need any of that. You just need height, weight, figure out the potential energy, we're done. That's energy. Got it? So what we do here is we would say this much energy, and then it will stop around here, this much energy. We can differentiate, and we'll get the total. Okay?
What are the scales on that
So
actually?
the scales on this are in foot-pounds and foot-pounds.
Okay.
We don't actually use this as a way to measure it, but it tells you the amount of energy here and the amount of energy at the end.
Okay.
Because what will happen is, if you ever use a scale in one of these, it'll go as far as it goes, and then it'll come back because it's like a
Gotcha.
pendulum. And so wherever this stops, that was the maximum potential energy on this side. Right? So that's what you're calculating.
You just take the difference.
Yes, exactly. Okay, so how the machine works. So this is all the background pretty much. How the machine works is we're going to do a velocity test here just to show you this is without any impacts. We're going to hit next on this, and we have 30 seconds from when that starts. It'll count down. What we do is we stand away here, we lift this pin up, we put it in 2. Okay? We take the lever, we bring it all the way to release. There's the pendulum. We then take this pin, bring it all the way here to break. It says break over here, right? Now, very important, when you pick this pin up, put it in 2. Do not pull the lever without, because if you pull the lever past this, you'll start to break it. And then you'll have more, your energy is going to go to the brake also. So your friction will be higher, you won't get the proper energy reading, okay? So carefully, one step at a time, 1 into 2, then pull. Then take it out of 2, put it in the brake, all right? When you're done, you bring it all the way back to latch. You take this, you put it into 1, all right? Oops. There you go. You put it into 1. Okay, that's it. I will do the rest, but from there, you're done. We'll pick up the samples once it's stopped, all right? That'll be everything. To reset it, I will lift it up at the very end here because this will require the least amount of force. Sorry, my moment arm here. So putting it over here rather than trying to lift it up from over there makes more sense. And then we are set, okay? You can see this is where this plastic ended as well. This would be the sort of thing. This has almost no energy loss. That's where it would end up. When we actually do an impact, you'll see it doesn't go as high. Okay? Any questions? Okay, so to put the samples in, we've got the 3 samples. Where's the other one? Where's the steel sample?
It's right there.
We get all 3 samples. The way that we do it is we use this. So we take this triangle right here, the center one, and we put it in right there, into the center. Okay? If it's liquid nitrogen, so you can't touch it,
Thank
you
you.
just line it up like this, it'll just fit right in. You pick it up. You keep your head away from it. Lean down if it helps. Line up your arm with this. This piece will fit perfectly right here, okay? So you put it right in the center, right? Then you put it up against the wall. Make sure that it's aligned, and then you need to slowly, while it's in place, you need to slowly, let it go. Now, it moves when I did it. So what I'm gonna do is I'm gonna pick it up again. And this will take a bunch of time, so we'll do it a few times until we get it right. But you need to pick it back up, triangle, there we go. Put it there, and then once it's in place, you need to slowly let go and make sure that it's not moving at all. Like that should not move. We want it directly in the center for that, for the impact to be right there so that it hits the thing. Okay? Got it? So we're gonna do that for all 5 samples.
All right.
Put it back. Now, we have 5 tests. Someone can do it twice or multiple times. Up to you. Who would like to start? Start? Okay, I need someone else to put the measurements in. So give me 1 second.
Which one should we start
We're
with?
gonna start with the steel. So give me 1 second. We're gonna run an impact
The
test.
red one? No.
This is aluminum. This is steel, aluminum, cast iron.
I think I was like, this is nope. I'm like,
Steel sample. And then I ask you a question. Oh, so when you pick it up, make sure that it's on the ground. When you pick it up, in the triangle, there you go. And then start putting it over there. Bring that up. Look at 2, yep. And then let go carefully. Now it moves a little bit.
They still require a lot of repetition.
There we go. Very nice. Okay.
Good stuff.
Energy sensing is where if the material is very ductile, it can absorb all the energy, so it's not necessarily will go to the other side, right?
No, but we still know the amount of energy. The reason we have a sensor on there is so we can see the energy at any point during the impact.
Okay.
We'll see it on the graph, but we want to see the full energy. We want to see the energy at the whole point. We don't want to just know the total impact energy. We want to know, see the whole graph is like, right? So that's what we're going to see. You'll see how the graph changes based on what material you're using.
So how would you get, so let's say the material is very ductile, right?
Yes.
And this, it doesn't go all the way to the other side like you were saying. So how would you calculate energy without having the, the sensor on there actually? Right,
If you calculate it, it'll come back up.
So no matter what, it will go through there.
Let's show you how it works.
Okay, sounds
We'll
good.
do one, and you'll see what happens. The answer is very easy,
Okay.
but in order to understand the answer, it's better that you see it.
Okay.
So you put the sample in, so come over here. You guys put it in, 369 for Walsh.
Yes.
So this is a Charpy specimen, just so you know that's what the notch is. Charpy? Charpy, yes. It's also in the lab manual.
Okay.
All right. You can find the dimensions for the Charpy actual notch online. So you'll need that to calculate stress concentration. Okay. So stand over there on the caution symbol, and I will walk you through it. Okay. So I'm in the next. Now, pick the pin up, put it in 2. Okay, you're good. Grab the lever, pull all the way to the pin. Alright, good. Pick the pin up, and move the lever to break. And then this way. I mean, you do not have to like it's okay, like when it slows down. I'm saying you're like standing there like
I was waiting.
oh yeah, no, it's
Because
fine.
the other ones you couldn't touch anything. That's what I was saying.
I'm saying, I would just say be careful about that. You can grab that sample. Okay, so this is the sample. Do you see what the answer to your question was?
Yes.
It bends and it just goes straight through. So it still will complete the impact because this is a lot of force. If this wasn't a lot of force, then you might have an issue. It might stop, but that we're not dealing with that. It just goes all the way through. So can you see what I'm saying? You see all of that ductility. Look at how much bending there is going on here. so much of it is bending. This is not anything like that brittle fracture, right? There's a lot of bending, and not only that, it also just didn't break at all, right? Like it looks a lot like the aluminum one, but unlike the aluminum one, it's not as soft, so it does break a bit. But you see that? All that ductility, it almost looks like a cross over there. Everything is bending in there. This is exactly what we expect from steel. This is why steel has a lot of energy, right? Because we've got steel and we've got a little bit of carbon in here just to give it some hardness, but this is what we expect, right? So the graph itself, just so you know, we've been going about 16.78 feet per second. That's what we've been going for. Same at the velocity test. So we're in fall 2019, 2019 fall. We are S1G3. This is our graph, steel room temperature. The red is the load, the yellow is the energy. So where's the impact? The impact starts here at 0. So until there's any load mentioned, there's no impact. When does the impact end? When the load goes back to 0. Okay? You will get this data later, and your impact will not start at 0 or end at 0. Your curves will not start at 0 and end at 0. So you need to show just these curves, just the impact forces. All right? So when it starts at 0 and then goes back to 0, that's all you need to show. It will keep going after that. No worries. So we have the load. The load goes up dramatically. What happens over here?
This is the point of impact, right?
No, the point of impact is here.
Oh.
What is happening over here?
Oh, that
When it
was
gets to the highest point on the other side?
No,
That-
so what is happening to the material here?
that was after the material bent enough for the arm to fully swing through.
So the material over here is not bent.
No, I'm not saying that part. I'm saying the very tip.
Oh no, I'm talking about this part.
Oh.
What happens here? Why is there this?
Uh,
Have you seen a stress strain curve for steel?
yeah. So I think it's when you it takes time, like less than a second for it to actually go through. But that fraction of a second, there's a certain amount of I don't know how I would explain it.
So the part before that, that's completely
So this
elastic, right? So you can
Yes,
go back,
it's
you go
exactly.
back and after that it becomes
So this is like the stress
Oh,
strain
okay.
curve. This is plastic. This is elastic. What happens here? Why does the curve now look different?
It deformed.
Yes, this is the yield point.
Okay.
The material has started to yield, but not only does it start to yield, but this is where the ductility comes in. You can see that it's such high ductility, it's actually bending and trying to absorb that energy, right? This is like the cold work that happens when you're actually trying to fracture steel. It actually gets harder for a little bit, right? While that ductility absorbs more of the load, and then it drops. What's going on here? It's broken, it's fracturing, and then the energy just sort of falls out. So this is the whole impact. At this point, it hasn't broken through. This part, it starts to bend, and this is completely fractured. Understand? This is the amount of energy. This is total energy. So this is the amount of energy that is being put on it. You can see that over here, it's linearly going up, but then it starts to drop down because now it's fractured. Now it doesn't need as much energy. Okay? So for this impact, we are looking at about 8 milliseconds. All right? This is milliseconds, not even a second. All right? You saw how fast it went. 8 milliseconds and about 51 foot-pounds, I guess. Okay?
So is there a significance in that intersection right there?
And which intersection over here?
Yeah.
Between the energy and-
Or is that just?
No, just one. It's two different graphs, but on the same
Oh,
thing.
okay. I see.
And it took about 3,200 pounds of load to actually cause this, to finally cause the fracture itself.
Just one more time. What is the yellow curve
The
again?
yellow curve is energy. This
The
is
energy.
foot-pounds of energy. This is coming from the load sensor, right?
Okay.
As well, like we calculate it based on the cross section.
Yeah.
Which we have, right? So we use 51.74 foot-pounds of force for actually energy. So that would be the difference between the two potential energies.
Gotcha.
Okay? Any more questions? So 8 milliseconds, about 3,200 or so pounds of force, and 50 foot-pounds. And we will compare this to when we see this again later.
So we for this, it took about 50 foot-pounds to actually.
To break it, yes.
Okay.
To fully break what we've
Yeah.
done here. Yes, here. Put it over here. You guys good? Okay. No problem. Okay, so this is the first sample. Who would like to do the next one? Actually, I put it here and they use it for hardness today.
It needs to be perfectly centered.
Yeah. It needs to be perfectly aligned this way,
Yeah.
as well as back up against it. If it's not perfectly aligned, then your impact will not be straight on. It'll move it back first. I'll do it again. It's too fast. most frustrating thing about this experiment? Oh, it moved. Looked perfect up until it moved.
So how are you guys aligning it? The indentation. What do you?
It has to be up against the wall and on the ground.
Yeah, and that fits perfectly between those two.
Okay.
So you can get it at almost exactly the same spot each time.
This is actually more difficult than you made it seem.
For me?
Yeah.
Well, I mean, I have been doing this a few times. No, you just gotta you gotta be patient with it. Like once you're in place, then you just gotta carefully set it apart.
It's magnetized too.
No.
No. So lean it up against the back wall. You're not leaning it fully against the back wall, so it moves when you pull it.
Jahari, how'd you do it the first time?
My hands are pretty steady.
Wow.
Also, if you didn't drink any sugar or coffee recently. Because some days when I do this, I'm not steady, and it's usually because either I didn't have a lot of sleep or coffee. It looks good. Yeah. You good?
Okay.
Yeah.
All right.
Centralized, but-
Lots of practice. All right, you guys giving it in?
Yeah.
So, is it really that different? 374 and 3745?
Yeah.
Oh, wow. I mean, part of it is the calipers, right? The calipers have a limitation. And honestly, the difference between 374 and 3745 is
Exactly.
almost minimal, right? Okay, so go to next. All right, you ready? Again, I'm gonna walk you through it, all right? So just wait for me to tell you. Okay, so pick the pin up, put it into 2. Take the lever, bring it all the way to the pin. Pick the lever up, or pick the pin up, and then move the lever all the way to break. Yeah, there you go. Okay, grab the pin. So you can immediately see the difference here with the aluminum. It has definitely fractured, right? It's much more of a brittle thing. Yeah, you can pick it up. Sure. It's low enough that it's okay. Grab the other piece also.
What do you mean, why am I doing this?
Okay. Great. So, let me show you the graph while we're doing this so we get an idea. Here's our aluminum room temperature. So you can see the graph looks completely different.
Yeah.
Right? We're looking at just like a straight thing. There's almost no ductility looking over here, right? So if we look at the actual sample, we will see that there is some bending at the edges, right? But the center is a very brittle fracture. It's kind of rough. There's maybe slightly bending. It's not perfectly flat, but there's the ductility is mostly centered around the edges. And so that's what we're looking at. This is a much less ductile material than the steel. Obviously, it's also a lot weaker in general, right? This version of aluminum is much weaker than the steel. Not all versions of aluminum alloy are this weak, but this one is this 2024. And that gets reflected in the graph. It only took about 1,400 pounds to break this.
So what was the other one was 3,200 pounds?
The other one was about
Yeah,
3,200 pounds. It took only 1,400 pounds to break it. It only took about 8 foot-pounds of energy versus the 50 of the steel. And then this broke in a little over 0.8 milliseconds, whereas the other one was about 8 milliseconds. So you can see what the difference between a fully ductile, well, not fully ductile, but a ductile fracture and a brittle fracture is. A lot less energy in an impact, right? And there is still ductility here. So when we do the cast iron in a second, you'll see there's even less energy required because it's just almost no ductility. All right? Yeah. All right. Any questions? No?
Yeah, so I mean that's a lot of those ductile, right? So for like
Yes.
vehicles, they're not pure aluminum; they're composites, right? For the
Well, so first of all, this is one alloy. You can use other alloys, but
Okay.
yes, aluminum is prized not for its strength, but for its combination of strength and weight. Right? Because steel is technically stronger for the same amount of material, but steel also weighs more. The advantage to aluminum is if you can always add a little bit more to it, right, in order to gain more strength. So you can make this cross section bigger to make more strength. But it does bend. Aluminum definitely does bend, and if you use different alloys, like in a crumple zone, maybe you use a softer aluminum to try to get a more bending, right? Like you saw the original aluminum was 99%, and it bent all the time, right? So this didn't bend as much. You have to choose your material based on what your requirement is, right? Okay. So, oh, that's unfortunate. The steel broke. You saw
Hi,
the
bro.
basic idea, but it did actually separate. It was small.
Thank you.
I just picked it up when the weight of the other one broke it. It's fine. It was connected very minor. Most of the time, steel does not do that. Most of the time, it looks more like this. And steel is much more connected, but in this case, this one did.
So that one was just more ductile than.
Yeah, apparently. Samples are changed based on the thing, you know? Every sample's a little different, but you can still see the ductility. This you'll never see in any of the others. The main point still remains. Really?
So what are we doing with that one?
Cast iron the same. I need someone to put in the material for the cast iron here. Someone put the thickness in with him, please. For the cast iron.
Yeah, you wrote it down, right?
Okay. Yeah, you understand. Yeah. Nope, moved a little bit. There we go. Look at that. Want to practice? You can do it another time if you want. But you did pretty good.
Wait, you got it?
Yeah, be honest. It's a
Steady hand.
Today I'm feeling very steady, but like last week there was at least one day when I just did it multiple times. You know when you're feeling a little bit like more shaky, right?
No, I saw what you guys were doing, and I didn't understand before when you guys were like.
You've got two surfaces. You've got the bottom and the back, as well as the so you've got all X, Y, Z controlled, right?
Yeah.
You got that. That's exactly the point.
Yeah. So once I saw that, that's
Yes.
how I was saying.
Exactly. See, it makes sense when you do
I
it.
tried to open it up, like, you know, just
Yeah.
the and it just like, oh. You know,
No,
twisted.
so,
So it's like-
I put this here so that because it was like before it was like
Okay. Stand by the caution. Okay, I'll walk you through this. Okay, pick the pin up, put it in 2. Lever to 2. Pick the pin up, and bring the lever to break. See, once you actually get it, it's pretty fast,
yeah.
right? We've already done 3. There's only 2 left in the whole lab.
And the other bolt are in the
Yes, that's the other 2 that we're gonna do. Okay. So I'm gonna let this break. Wait a second. Yeah.
Is there a reason for the graphs to be like?
Yeah, so that's the voltage.
Oh,
The voltage is not. You ever measure voltage something and it goes like that? The actual graph is good, but like it's a little shaky. When you graph it in like Excel or MATLAB, it'll be very fine. You know. Again, we start from 0, end at 0. That's the graphs. Your data is going to be different, so make sure also to keep an eye on the units. The loads are in pounds, the times in milliseconds, the energies in pound force. It's all in the data, just so you know it. What happened was I was giving people this data and they were having trouble with it. You don't need this. You just need the curves. Right? That's all you need for the lab report is just these curves, pretty much. But from 0 to 0 on the force. So it took about 430 pounds to break this. So even less than the aluminum, right? It's a very brittle fracture. 0.83 foot-pounds of energy. Right? It's like a magnitude. It's like 10 times less in that respect.
Were you saying 430?
430 pounds of force, but 8.83 foot-pounds of energy. Right?
Oh.
2 different units here. And then the fracture was done. So the other one was a little above 0.8 milliseconds. This is like 0.28 milliseconds, right? This is even less. But it's just dramatically lower. And it's not because this isn't a strong material. You've seen cast iron, right? Cast iron is fairly strong, but impact is really its weak point, you know? Some materials are better at tension, some materials rotation and stuff like that. Some materials are just bad at impact, right? We love hardness, but if you put your phone in that device, it will just break, right? Like your screen will just crack because the glass is really hard and it's great for standing up to scratches, whereas this might not stand up to scratches as well. But you know, every material has its ups and downs, and you got to sort of work with that. Or make alloys. Okay. Any questions?
Yeah, concrete is like really brittle. So like,
Yes.
how do they strengthen that to make it less?
Steel rebar.
Oh, shit, yeah.
Concrete is actually really strong at compression. It's a very, like you can compress on it, like we're standing on it right now. It compresses really well, but it does not handle tension very well or bending. So what we do is we add steel to it because steel handles tension and bending really well. So that's really it. You have to take concrete and steel is almost like a composite, really, right? You're taking the strong things, the strong suits of one thing, and helping it with the strong suit of the other. The steel, for example, will not buckle when it's being compressed because the concrete all around it is protecting it. Right, so the steel is depending on the concrete also,
Oh.
not just to hold it in place,
Yeah.
but also because the concrete just doesn't like to buckle, right? That's why we have concrete columns everywhere. If you want to make steel columns, you have to do I-beams, but that's not what we're doing there.
Yeah.
Any questions?
That's good. That's a good question.
It's a good question. That comes up. Doesn't really come up in this course, more in mechanics and materials.
Yeah,
but
I remember now.
yeah, the basic idea is the same. So let's keep these separate so you know which one is which. Steel, aluminum, casting. Now we're going to do the liquid nitrogen. Who would like to go first? Decide amongst yourselves.
You have to say
Steel,
names.
liquid nitrogen.
Yeah,
Or you did it yourself.
she's got it.
Okay, damn.
There's 2 liquid nitrogen samples.
Do I just grab them or?
No, not with your hand.
No, I know not with my hands. I meant with this.
Yeah, I think it's pretty
Like I meant with this.
and width for steel.
With
Actually, should we do steel first? Or aluminum? Let's do the aluminum. The aluminum doesn't change very much. So Ln2, put in aluminum with thickness and width. Okay? So aluminum, that's going to be the red one. All right, you ready? I'm going to take it out for you, and then once it's here, it's all yours. All yours. So for steel, I don't really pay attention to the red or the blue. I'm just looking at the color because obviously it's a lot lighter than steel. Okay. Obviously, do not touch this with your hand. It'll actually frost over a little bit from the humidity in the air here. Oh, I don't know. Go this way. I don't know.
oh, you had it.
I had it.
Yeah.
Yeah.
There we go.
There we go.
Okay. Same as the other one, just don't touch the sample. 1374, 1375. Great.
That one is aluminum?
Yes, this is aluminum. This should not show much of a difference. Actually, this will get maybe slightly more ductile, but very slightly. Do that again?
Wow.
Do it again.
Yeah, do it one more time. It's more that just that I want to see it. I wasn't really.
Yeah, you got it yours. Just get it.
Very good. Very good. See?
Good stuff.
Fantastic. Someone could be a surgeon.
I was gonna be a surgeon. That's what.
Oh, well, great.
But then,
Be
yeah.
perfect for it.
Major
You want to
surgeon.
finish it off?
Aluminum. All right, so stand by the caution. Is there someone who hasn't done this yet? Oh, have you done it yet? So you want to do the steel?
Yeah, it's just-
Do you want to do this one?
it's good.
No, so wait. I have to actually hit the next thing. Okay? Okay, pick up the pin, put it in 2, lever. Alright, move it to break. And then we wait. Don't, yeah. I got you. How we're looking at it, I was gonna say, like you can look at it, but
Don't reach for it. Pow.
we'll be able to touch it. It's not yet. We can touch it later. So I'm gonna put this over here real quick.
Sorry about that.
This is the aluminum. Welcome to take a look.
It's a little more ductile.
Don't.
So this one has been a lot more ductile than I expected.
Yeah.
It usually doesn't change very much, but it's surprisingly ductile there. So, ALLN2, this is very
Oh,
ductile.
yeah, wow.
Very interesting. All right, so we're looking at, good, AL room temperature and ALLN2. So, I have both of them open here. So, based on the graph here, so this was the original room temperature. You saw about 1,300, almost 1,400 pounds or so, 1,420, I think, something like that, 1,410 pounds of load. Sorry, we're still less than that. We're about 1,300. So you can tell it's the same material, right? Same amount of load, amount of energy, 8 foot-pounds, 8 foot-pound force of energy. About 22. This is a really ductile sample. It usually goes to about 12 or so, but so depending on the sample, it will change a bit. This one is quite a bit more ductile actually than it originally was. This one took about 0.8, a little bit more than 0.8 milliseconds to break. This one took, doesn't have a unit here, but closer to 1 millisecond to break. Okay, so we're actually looking at an increase of ductility. The load is about the same. It actually dropped a little bit load-wise, but in terms of amount of energy, it was actually increased. But the important thing to note here is that it's not as huge a difference as what you're about to see with the steel. Right? The aluminum difference is a difference, and most of the specimens we've tried have been only a little bit more. This one is kind of unusual. This one is a lot more ductile. But the thing to note is that it isn't as much as what a difference is what the steel was, right? You'll see in a second what happens to the steel. The aluminum, on a relative scale, this is barely noticeable, right? Barely noticeable. It's the same amount of force. The energy is just different. You know,
What
but only
might-
like twice.
What might be a reason why?
Well, it depends on the alloy.
Okay.
The alloys will change it. Some alloys actually do get stronger at colder temperatures.
Okay.
But the point is that we are not brittle on the aluminum.
Yeah.
At this point, like we're not at that ductile to brittle transition point. But aluminum was never that ductile to begin with, right? You can see over here we do have a similar thing to the steel. This is after it's yielded, but it hasn't actually fractured yet. Okay. So the important takeaway from this is that even though there is a pretty substantial difference here, it's not as big a difference as what we're going to see with the steel. So this isn't as big an effect. Okay. So now we're going to go an impact test again on steel. Drop. It's not as low as the aluminum got, but it's a huge difference compared to what it used to have. Okay.
Ductile, but broke very quickly.
Sort of see. It looks like this now, although because the steel didn't actually. It's surprising. This steel usually doesn't break apart, and this aluminum usually doesn't get this ductile. So you guys have both very interesting samples. That neither of them sort of followed it. Can I have the pin? So let me reset this, and then we will look at the graph. Okay. So the graph on this. So this is the steel at room temperature at the top. This is the steel at cold. So only 1,200 pounds versus 3,200 pounds. So immediate difference on the pounds.
Almost like aluminum.
What?
Almost like aluminum.
1,200? It's actually less than the aluminum.
Yeah.
The aluminum
It
was
was
at 14, and then even at cold LN2 it was at
It was
1,300, right? 50 foot-pounds of force, 2 foot-pounds of force. So the aluminum changed, right? It changes a little bit. The steel changes dramatically, like a really big difference. And you notice the ductility is still there, but it's it's so much more brittle still.
So it took 41 pounds to
No, it took about 1,200 pounds.
1,200.
You measure at this point.
Oh.
At the end here is where the total amount of load is. So it's around 2.42 foot-pounds.
How much was for this one?
51. We look at it when the load is now at 0. It's about 51. So you'll get these graphs. You can also see that this impact, like this curve, looks a lot more like the aluminum and cast iron curves, whereas originally it looked like this. So this is the huge difference that steel makes when you drop the temperature.
So yeah, for steel and below freezing, generally they just get weaker. Generally,
Well, they get more brittle.
brittle.
Yeah, that's exactly what's going on. And actually, some alloys, it depends. This alloy, I think, this starts happening around freezing, just like 0 degrees. So even just slightly below freezing. We drop it to negative 200 because we definitely see the effect. But even at 0 degrees, you already have to deal with this, right? So you got to be careful. The steel is a nice material, but it's got problems. Its weight is an issue, and it's not so great when it comes to temperature changes. Right?
I don't mean to go on a tangent, but so what about like our space rockets or what we send into space?
Yes.
Do they reinforce it or do they they use different?
Depends what they make them with. If they're going to use aluminum, they're going to use steel, which steel is very heavy, so you want to use it as minimally as possible. They will reinforce it as required for anything that is structural. Also, because once you're in space, it's kind of cold. Right?
Yeah.
Is that's what you mean? Yeah, they will reinforce it. They will also use different alloys. It's not just plain steel. They will use different. This is just 0.2% carbon, but you can change the alloy depending on what you need for what purpose. And then when it comes to space, they've got the budget and what's it called? Weight is such an important thing that they will try to use as much aluminum and titanium and composites as they can to try to deal with that. So steel alone isn't always used. Depends on where it needs to go. Usually places that aren't so temperature sensitive, you do it. If you do
Finished?
what?
Have you finished your experiment?
Yeah, the experiment is completely done. We finished everything. You guys, you can take a picture of the. So what you should do I'll get you the data from the computer, but otherwise the experiment itself is done. Take a piece of paper, put the samples on the paper, and then right next to the samples like aluminum, steel, cast iron, and then aluminum at liquid nitrogen, or aluminum cold and steel cold, and then take a picture of that so you can see all the different pictures. Samples. I will get you this curve data as well. I just need someone's flash drive.
Just to make sure, this right here, it means that for room temperature steel, it took 2 pounds of force.
Which one is which?
Steel, aluminum, cast iron, steel, aluminum.
Okay.
I've been taking pictures of them, so it's.
Okay, cool.
That's the force. I mean, you can see this is like a 60-pound weight, so that's not
Cold?
Fucking touching it, yeah.
You touch it? Is it
You
cold?
do it yourself, but if you impact something,
I don't really feel it that much.
That's kind of cold.
I mean, this one's still kind of cold.
Yeah?
Any more questions? You guys want to ask
Not
questions?
exactly related to this, sort of, but you call Tesla, not really
Stainless steel. I was going to bring this up. So stainless steel. Why are they using stainless steel? So stainless steel, first of all, is a slightly different alloy steel. They're using it because its melting point is extremely high, and they have reasons, mostly for
So
reaction.
because most atmosphere is so thin, they like you said use it for reactors.
No, in the Earth atmosphere is not thin. They're talking about Earth reentry. That's what the steel. That's why they chose the steel.
Okay, I thought it was, aren't they going to send it to Mars?
Right. Well, that has its own challenges.
Right.
I'm saying, yeah, they're designing the rocket so that. You can
Oh,
do
actually, that would
Earth
be cool,
atmosphere.
right?
You do the Earth atmosphere, the Mars atmosphere is
No,
not.
I've been taking like individual pictures of them like that too.
Oh, like when these are showing? Oh, cool.
Whereas the Earth's atmosphere, you can just slow down with the atmosphere. But that's why.